Welcome all. Welcome to this fourth webinar of the BD-RIS webinar series 2025. It's my great pleasure to introduce today Professor Ertugrul Basar from Tampere University in Finland. Let me briefly introduce him before giving him the floor. Professor Basar was born in Istanbul, and he received a Bachelor of Science degree from Istanbul University in 2007 and a Master of Science and PhD degrees from the Istanbul Technical University in 2009 and 2013. He is currently a professor of wireless systems at the Department of Electrical Engineering in Tampere University in Finland. And before joining Tampere University, he held position at Koç University and Istanbul Technical University, and visiting position at Princeton and as a visiting research collaborator, and Ruhr University in Bochum as a Mercator Fellow. Professor Basar's primary research include 6G and beyond wireless communication systems, multi-antenna systems, index modulation, RIS, waveform design, zero power and noise-driven communications, software-defined radio, physical layer security, quantum communication systems, and signal processing and deep learning communication. And he has published hundreds of journal publications and received around 19,000 citations. So approximately the talk is expected to last 50 minutes, after which there will be a brief Q&A sessions. Feel free to type your questions in the chat, and then eventually we will pick some of them, or you will raise your hand at the end of the talk. So enjoy the talk, and Professor Basar, the floor is yours.
Okay. Thank you. Thank you, Matteo, for the kind introduction and also for the invitation. So let me share my screen. So I hope it is visible now. It's full screen now. I hope you can see it. Okay. Okay. So I hope you can see my screen. So let me start. Okay. My name is Ertugrul Basar, so Professor of Wireless Systems and IEEE from Tampere University. So in today's talk, as Matteo mentioned, so around 40 to 50 minutes, I will discuss about emerging carrier technologies because we have been doing active research in this field for maybe more than 6 to 7 years. I don't know. So it was even before the COVID times when we started our basic research in this topic. So in today's talk, so I will cover the most recent developments in this field. So, and also we'll try to provide a perspective for 6G and beyond, and also cover the recent studies performed in our group in this field. So actually, probably you are familiar with this two circles in the past 2 years, because it has been almost 2 years since ITU, International Telecommunications Union, published this 6G outlook and expectations. So as you can see, the famous 5G triangle is at the inside, and we are expanding into a hexagon by 6th generation wireless networks by adding immersive integrated sensing communications, AI communication, and ubiquitous connectivity to the equation for the first time. So in this context, in the past couple of years, we have been trying to position intelligence services, so particularly targeting these 6 pillars. So 3 actually comes from 5G and 3 new pillars, as you can see. And we're trying to find some killer applications for intelligence services so that we can support these usage scenarios of IMT 2030 is actually the official name of 6G and IEEE framework. And as you can see, we expect some enhanced capabilities for IMT 2030, as you can see in terms of, peak data rate, experience data rate, spectrum efficiency, mobility and latency, and so on. So in this context, we're trying to, position intelligence services for 6G and beyond. So actually, maybe we will discuss in the end, but right now we know that intelligence services will not be an integral part of first releases of 6G. This is what we understand from recent standardization, discussions and in the, bodies. But at least we're trying to understand how we can, use intelligence services in such a way that these new capabilities and enhanced capabilities of sixth generation wireless networks and beyond can be supported. And we did, a series of works, including security, including positioning, increasing the user experience and so on. So in this context, I will just try to provide a brief overview and also cover the recent developments in this field and recent RAS architectures. Actually, it was last summer, where reconfigurable intelligent surfaces has been defined as an emerging technology by World Economic Forum. So with some colleagues from our field, I think, contributed this article as far as I remember. So actually, what's an emerging technology? Emerging technology is a technology which has the potential to reshape industries, economies, and the societal structures, and providing some opportunities, as you can see. Actually, these were the list of, these emerging technologies, and as you can see, the configuring intelligent surfaces, high altitude platform stations, integrated sensing and communication. These are all related by communication. So it's also a nice surprise to see these three communication technologies in the list. And as you can see, with using intelligent services, we can enable smart factories. We have been working in this sense. Wave domain information processing, we have been working on that. So mathematical technology and application is a little bit beyond the scope for our group, but at the end of the day, using prototypes and so on, we have also gained quite experience about how to, obtain these intelligence services in real life, how to realize them and so on. Enhance sound and vision, and so this kind of emerging and exciting applications, provided by intelligence services. Actually, we call it wireless 2.0, so with intelligent radio environments where, similar to software-defined networks in fifth generation wireless networks, the idea is to provide some sort of a software control into radio propagation, so that we can customize the propagation of radio waves using some sort of software. As you can see, this is an intelligent surface. You configure it and you focus the signal to the blue user, but in a different time instant, you reconfigure it, and right now the signal is focused to the red user. Just this is an illustration. So what is an intelligent surface? As you can see, this is an electronically controlled with integrated electronics and have these unique wireless communication capabilities, and it's some sort of electromagnetic material. It's a real-world prototype, by the way. The prototype developed by Greenerwave, I think almost 3 to 4 years ago, a French startup company that we have been using actively in the past couple of years in our practical experimentation studies. So as you can see, there's 76 unit cells, and each unit cell there are 2 pin diodes, and we adjust the on-off studies of these pin diodes in order to realize this, unnatural electromagnetic, features. I say actually the idea is to somehow control the signal propagation so that we can fight with multiband fading and probably maybe in shadowing in some cases. Of course, path loss requires, site planning and, more higher level coordination. But the idea since the old times use intelligent surfaces, particularly to cover those shadow regions and fight with multiband fading so that the user experience can be improved. So yeah, we briefly discussed about standardization, as I mentioned. So actually, it is interesting to make this connection with network control repeaters, because network control repeaters right now are part of 3GPP specifications included in release 18. So yeah, probably it is there in release 19 as well, so we need to check. But it is an in-band RF repeater used for extension of this coverage, as you can see. Of course, there's multiple antennas. It has this amplification feature. It is deployed in single stationary environments, and it is transparent to the user equipment. So this is also important. So in terms of user equipment perspective, and as you can see, there is a G0B to repeater link and repeater to user equipment link, and it enables them simultaneously, as you can see, and there's a control link and backhaul link. So it's a sophisticated device, actually. Why we are making this comparison? Of course, network control repeater is a couple of steps beyond intelligent services, because it has this control and backhaul links, and it has this amplification feature, multiple antennas, and so on. Yeah, of course, it is more complex, more power hungry, but I think operators and vendors took this conservative choice to include network control repeater instead of intelligent services, because it provides more functionality, more flexibility in the network design, and so on. So as a result, actually, the inclusion of NCR to the standardization overshadowed a little bit intelligent surface in the past couple of years, but still, I think for the upcoming release of 6G, we will probably find some killer applications for intelligent surfaces. I will also try to touch this by the end of this presentation. So in which scenarios we can use intelligent surfaces, maybe in later 6G releases. So this was a comprehensive study which we completed by some collaborators last summer. So potential RIS applications. So actually, we envision since the old times to use intelligent surfaces for scarcely covered areas. So in this context, there have been quite interest in the literature to equip some high platform stations by intelligent surfaces. I know there are some maybe operational challenges for this, but it is a I mean, interesting approach to provide coverage to these scarcely covered areas. But in my humble opinion, it's not straightforward. But I think one of the clear applications of the intelligent surface in later release of 6G might be outdoor to indoor coverage extension. For instance, particularly this is critical at higher frequencies, millimeter wave or maybe mid-band frequencies above 6 gigahertz, 7 to 24 gigahertz. Because these signals cannot penetrate through windows very efficiently. So we can design this transparent intelligent surface that the windows or maybe some kind of surfaces like this close to windows so that the user experience at the indoors is not affected too much by this significant attenuation. So when the signal passes through the windows and so on. And then apart from that, we have been working, for instance, for smart factories. We have some studies and results on that, interesting results that I will show. IoT devices, of course, so energy harvesting devices, even physical layer security and so on. So these are the interesting potential RIS applications when we look forward to 6th generation beyond wireless networks. Actually, the technology is not completely new. It has a rich history as well. So we started to work on this topic around 2019, before the pandemic times. So in my first papers, I used large intelligence surface. Then in our, I think, first survey paper. So where is it? This one. This one. So at that time, I remember our discussions with Professor Direnzo, the whether use reconfigurable intelligence surface or large intelligence surface. Then we made the consensus on reconfigurable intelligence surface, and we coined this term in 2019, reconfigurable intelligence surfaces. But before that, there's large intelligence surfaces, hypersurface tiles, and even before that, these tunable meta surfaces, some early prototypes, as you can see from 2014, 2015, even intelligent walls in which can interact with the upcoming signals. And even before that, metafilm in early 2000s. These are the initial concepts, but particularly after 2019, this turning point with the new terminology of reconfigurable intelligent surfaces. And after that, we had these interesting developments in this field as well, like holographic MIMO antennas and intelligent omnisurface or simultaneous transmitting and reflecting intelligent surfaces, in which can both transmit and reflect the incoming signals. And even more recently, amplifying intelligent surfaces, beyond diagonal intelligent surfaces, and so on. So these are the most recent developments in the field of intelligent surfaces. Actually, again, another invited paper from last year in Vehicular Technology magazine, in which we provided this comprehensive overview of emerging RIS architecture. So what are those? We can have intelligent surfaces, still passive, but some sensors embedded. And these sensors, of course, have access to RF chain for additional signal processing. We can use this sensor embedded passive RIS for maybe for channel estimation or sensing the environment, sensing the user location, and so on. So it is possible. Of course, it's more complicated compared to fully passive one, but at the end of the day, we need to add some sort of intelligence. And since the early times, I remember some papers, even in COVID times, proposing this concept with embedding some sparse sensors on the intelligence surface. So now this architecture is, of course, more complicated because it's a hybrid RIS. What is a hybrid RIS? some part of the incoming signal is down converted using some radio frequency chains for additional signal processing and so on, and some part of the signal is reflected, so it's some sort of a hybrid surface. It performs both, again, signal processing and both signal reflection. So of course, a more advanced architecture, but it is more complex compared to fully passive intelligent surfaces. Two emerging architectures, maybe we can add beyond diagonal intelligent surface to the mix as well, stacked intelligent meta surface or three-dimensional intelligent surface. We have this transparent layers which are separated by only a couple of wavelengths and which are generally very close to transmitter, so that we can enable wave manipulation effectively with simple cost and in order to provide much strong functionality compared to traditional intelligent surfaces. There has been quite interest in this field in the past couple of years. Star RIS, simultaneous transmitting and reflecting intelligent surface, again a single layer of transparent intelligent surface, so that the incoming signal not only reflected but also transmitted at the backside to enable 360 degrees full coverage. So how this is possible? It is possible by a transparent surface. Maybe I did not mention, but for instance, for this prototype, there is some sort of a metallic backplane, so that the signal hits, but it does not penetrate through. It's reflected back as much as possible. But in this transparent surface, this metallic backpack is we don't have this metallic backplane, and with this specific architecture of unit cells, the signal can pass through. So there are also quite interest in this field and some novel algorithms to utilize this star RASs. So actually, I mentioned about beyond diagonal RAS. I'm sure even the attendees or maybe later watchers of this video on YouTube quite familiar with this. Beyond diagonal RAS is also a quite emerging and exciting new concept in which there are some connections between elements, so that the interaction of the RAS with the incoming signal is much more flexible, and you can have this interaction matrix in non-diagonal architecture, so that you can enable more functionality at the receiver side. So it's the main motivation of beyond diagonal RAS. As you can see, it's a fully connected architecture in which each element is connected with the other elements. If, for example, there are only 4 elements here for illustration purposes, and it's a group connected architecture. Of course, there is a complexity performance trade-off. There are 36 elements, 9 groups, and there are 4 unit cells in each group, so that, for instance, these green ones are connected to each other, pink ones are connected to each other, and blue ones, and so on. So it's a more simple architecture, less complex circuitry, but its performance, of course, is worse than fully connected beyond diagonal RAS. So yeah, Professor Bruno from Imperial, so they did quite a lot of work in this field in the past couple of years. We have been also working with some colleagues on amplifying RAS architectures in the past couple of years. So actually, if you look into the circuit architecture, how you can achieve amplification by using a tunnel diode driven by a DC voltage generator. In this case, you will have negative resistance with this tunnel diode, and you can enable amplification. Amplification might be possible for the outgoing signal. So what is the price paid for this? You have this power source, so you need to consume power each unit cell. So actually, a couple of years ago, we developed this architecture with 2 intelligent surfaces back to back. The signal is collected by the first one, amplified, then given into the second one. This is, as you can see, there's only a single amplifier here. Therefore, the power consumption of this thing and complexity is much lower compared to this tunnel diode-based architecture, in which you need a power source for each unit cell. So it is a more power hungry, more complicated, and more costly, but this is a more low-cost solution, more energy efficient solution that we developed a couple of years ago in this field. And we also did quite a lot of studies in the upcoming times. Actually, from a signals and systems perspective, since the early times, we have been trying to understand how intelligent surfaces manipulate the signals on the go, we have this incoming signal and outgoing signal, as you can see, I mean, modified phase and modified amplitude probably. And this RIS interaction matrix is the collection of these phase and amplitude terms. As we said, for a classical passive RIS, it's a diagonal n by n matrix, with n is the RIS size. But for a beyond diagonal RIS, it could be a banded matrix, some non-diagonal non-zero entries as well. So when we define, derive the receive signal to noise ratio, we see that the receive signal power is proportional with n squared, with n becoming the RAS size, but we have this double fading effect, unfortunately, which limits the range and, actually usability of intelligent surface in certain applications, because the signal passes through this both paths and it has this multiplicative fading effect, so it suffers from double path loss from transmitter to RAS and RAS to receiver. So the idea actually since the early times, the channel is the part of the communication system which is unwilling or unable to change. So a saying from Professor Popovsky's book that I took. So we're trying to challenge this status quo so that we can maybe manipulate the signals on the go. Since the early times, we have been trying to define some interesting applications for intelligence surfaces. So one of those is, this transmitter type intelligence surfaces. So in transmitter type intelligence surfaces, the RAS is a part of the transmitter. So it is driven by the data source and it manipulates the signals on the go. So as you can see, an unmodulated carrier hits to the intelligent surface. Actually, those stacked intelligent meta surfaces, those also operating in this context. The RAS plays the role of an access point, some sort of. It creates virtual constellations, but it has a very simple transmitter architecture with no mixers, filters, or radio frequency chains. So when I first started to work on intelligent surfaces, it was, I think, in late 2018, early 2019. In my first architecture, in my first paper in this field, appeared in UCNC 2019. This was the concept that I developed theoretically. So can we design a virtual constellation by an intelligent surface? Independently from me, I saw that some colleagues from Southeast University, later we also built a very strong collaboration and relationship with them. They developed the same concept experimentally, in which by illuminating the programmable metasurface by an unmodulated carrier, and they were creating this RF chain-free 8PSK wireless transmitter. So it was interesting to see that the concept is developed both theoretically and practically at the same time. So in the following years, we did a bunch of work. So these are all studies. Therefore, I want to, pass through these slides quickly so that I can focus on the recent studies. We developed some over their MIMO solutions, over their, NOMA solutions, by dividing the intelligent surface, by using star intelligent surfaces, by using hybrid intelligent surfaces with joint active and passive LMS, and so on. So we export this new architectures from MIMO and NOMA recently, and also over their beamforming, in which we do the beamforming by active intelligent surface. In order to do this, you need an active intelligent surface, so that we illuminate the intelligent surface again with some unmodulated signals, so that the beamforming is performed by the intelligent surface. It's also possible, as you can see in this attached study. And again, it's very interesting and old study. So a couple of years ago, we tried to perform equalization on the go by an intelligent surface. How we did this? We adjusted the intelligent surface in such a way that the first path, the strongest path, is boost, while keeping the other paths the same. In this case, because if the first path is very strong compared to other multipaths, we have a flat fading channel. It's a frequency selective channel, as you can see. If we enhance this first path, then we can somehow emulate a frequency flat channel. So this was the idea, to convert this frequency selective channel from frequency flat one. So even more recently, we have been actively working on advanced modulation schemes as well, using intelligent surfaces. Again, this maybe tip of an iceberg. We did quite a lot of work on combining index modulation and those advanced waveforms such as OTFS and so on, to design advanced architectures, including intelligent surfaces. For instance, here we have this receive special modulation. We activate receive antenna indices by, again, dividing the intelligence surface and performing antenna index selection. This is even more complicated scheme. We have this code index modulation. So we select not only antenna indices, we also select spreading code indices. So it's some sort of a spectrum scheme, but also employing index modulation because receiver tries to find which spreading code is selected. Again, we implemented this scheme using a intelligence surface with two parts, as you can see. And even more recently, OTFS is an emerging waveform right now, a candidate for 6G, later release of 6G as well. It will not be part of the initial release, but it's particularly for high mobility environments. It provides significant advantages compared to OFDM. So we realized and RAS aided OTFS with index modulation scheme recently with some colleagues as well. So in the past couple of years, by using these RAS prototypes, we gained quite experience on practical experimentation. So how to, use these intelligence surfaces. The actual result of our efforts appeared last year in Open Journal of Communication Society. So as you can see, we have the transmit antenna and receive antenna with RAS. So and with certain test locations, particularly what's the main takeaway from here? When this setup is symmetric, the effect of RAS is not significant. As you can see, we can increase the signal power for a couple of decibels. But when this setup is asymmetric, as you can see, transmitter and receiver in asymmetric locations like this, in these cases, as you can see, we can increase the signal power up to 10 dB or even more. So this was actually a beautiful feature of intelligent surfaces. In later studies, we tried this offline code word approach, where we optimize the intelligence surface for a certain location. Then according to the user location, we select the closest reference point. So because otherwise we need to use some sort of iterative algorithm to optimize the intelligence surface. We start from the first element on and off, then jump to the second element on and off and check the received signal power to see whether turning on and off a certain element is beneficial for the received signal power or not. This is called iterative algorithm. So alternatively, you can divide the intelligence surface into parts, 2 elements, 4 elements, 8 elements, and you can turn on and off those elements. And as you can see, this reduces the overhead of those RAS optimization, and the performance is slightly worse, but you can still approach to the case of one-by-one searching. So this was the initial idea, that when we start to practice, make experimentation with intelligent surfaces. Of course, if you want to realize these intelligent surfaces, and maybe these surfaces might be network independent or dependent, depending on the application. In the network independent RAS case, the user actually provides some sort of RSSI feedback to the RAS, so that RAS optimizes his signal direction. So this was the experimental study that we performed again almost 2 years ago, compared to the case where RAS is off. Again, receive signal power is boosted significantly. This is again interesting study 2 years ago, probably the first study in the literature that considers physical layer security with intelligence surfaces. In this case, we have 2 legitimate users, Alice and Bob, and third user, hidden eavesdropper, and we are adjusting RAS in such a way that the eavesdropper hits to the noise floor after certain optimization iterations. We were experimentally demonstrated this concept in VTC 2023. And millimeter wave tests. Actually, this was a video, but it was playing, but I'm not sure whether it will play here. So it plays now. So yeah, I think millimeter waves is an area where intelligence source might be critical. And it's again a millimeter wave prototype for 28 gigahertz. And it has, as you can see, it is, as far as I remember, 20 by 20, 400. So it's in total 1,600 elements. As a result, the iterations are quite high, but the signal power can be improved by the 30 dB, because in millimeter wave, particularly, the line of sight is critical. But we cannot use this intelligence surface like this. We need to develop some clever algorithms such that And you don't need to try this, all the iteration on and off studies of these pin diodes. So, okay, so how can I jump? Okay. So multipath mitigation, again, a collaborative study with colleagues from Southeast University. We have shown that using different RIS architectures, it is possible to, eliminate the effect of multipath by using intelligent surfaces. Again, we did some tests again with colleagues from China using real-world 5G base station, and we will be able to again increase the receive signal power up to, as you can see, 5 to 6 dB in a real-world 5G test scenario. As far as I remember, it was 2.4 gigahertz in this intelligent surface. Again, a collaborative study. We developed some certain more realistic path loss models for outdoors, indoors, outdoor to indoor scenarios. Again, it's a big intelligent surface because it's designed for 2.4 gigahertz. We developed some path loss models, floating intercept and closing path loss models that fits to the measurement data. So what is actually floating intercept? Maybe it is more understandable here. Actually, in closing path loss models, we have this reference point. We consider the free space path loss at, let's say, 1 meter, 5 meters, 10 meters, and so on, and we develop the path loss model accordingly. In floating intercept models, there is no reference point. There is this floating intercept term, and it is optimized. This is very similar to long distance path loss model that we use in modeling path loss. N is the path loss exponent, X sigma is the shadowing parameter due to the environmental objects. And even more recently, again, with collaborative study with colleagues from Southeast University, with the same intelligence surface at 2.4 gigahertz, we developed the even more realistic path loss model considering RAS array gain. So as you can see, the earlier models, floating intercept and closing model, free space RAS model is the worst one, and the measurement data is the black one. And as you can see, this new RAS array gain aware path loss model approaches almost to the measurement data. So this is very interesting, actually. Probably this is, appeared because we passed this conference. So we considered the, energy efficiency of intelligent surfaces, because at the end of the day, intelligent surface also consumes certain power, and we try to develop some energy efficient algorithms so that the power consumption of the intelligent surface is minimized. So as you can see, the test scenario is for 35 gigahertz here for a two binary, again, on and off unit cell. So as you can see, the control circuit has a certain power consumption. So to have enable this on and off to encode zeros and ones to the unit cells. So we developed a method, as you can see, the blue one, EEPQ method, so that the power consumption is minimized compared to some traditional RAS control methods. So this is not new. So as a result, I will not spend too much time, but channel modeling, we have been working on this very recently as well for form factory environments. So this was a part of a European Union project in which we involved 6-year BRICS, so that we envisioned an RAS-assisted indoor factory environment, so that this, as you can see, the user equipments in indoor factory environments are supported by an intelligent surface, which is actually a part of an open radio access network architecture. As you can see, we have this flexing architecture coming from this ORAN, and we have this RAS control XApp and codebook generation XApp, which controls the RAS in real time. So we develop this model from ground zero with open run integration. So as you can see, there are different scenarios. We call this enhanced goal SIMRIS. So SIMRIS actually the original idea, that original simulator that we developed almost 5 years ago. Goal SIMRIS developed by the project partners, and we developed this enhanced version of it for indoor factory environments. So what are these SL parameters? Sparse, low height, dense, low height. These are, as you can see, some 3GPP taken from 3GPP standard indoor factory environments, and we perform comprehensive simulations within this framework, which we called ORIX, Open Run Integrated Intelligence Surface with XApps. As you can see, 5 scenarios here: room size, cell heating, clutter heights, and so on, clutter density. So this H is high clutter density, as you can see, and low cluster density, as you can see. In the scenarios and line of sight and non-line of sight scenarios, we took all these parameters from 3GPP standard and also use this RIS integration, not integration, RIS optimization techniques such as iterative method, quantized phase shift, and codebook generation, and evaluated the performance in this indoor factory environment at 28 gigahertz in terms of number of RIS elements, transmit power, RIS side length, as you can see, different frequencies, different indoor factory environments, different RIS types, continuous phase, 1, 2, 3 phase. So, and we have shown that, again, in an indoor factory environment at 28 gigahertz, an intelligence surface can be a useful remedy because it's a hostile environment with dense clusters and moving objects and so on. And compared to the case where there is no intelligent surface, we obtained remarkable, achievements in terms of data rates. Again, some recent studies from our group, plug-in arrays, actually some sort of an arrays in which certain part of the arrays actually illuminates the signal to a certain special segment, as you can see. So we envisioned this concept in order to realize intelligent surface in a plug-and-play manner to the network, so that it requires minimal, control from the base station side and user equipment side. This was an interesting study, again, from last year. And as you can see, compared to the, semi-passive arrays or blind arrays, of course, blind arrays is worse. Semi-passive arrays is the best. We try to approach the performance of the semi-passive arrays with this plug-in arrays concept, and we succeeded it in terms of bit error rate and achievable rate. And there is right now quite interest in the literature in movable architectures, movable antennas, pinching antennas, fluid antennas, so on. And we solved this gap almost 2 years ago and developed this spider arrays concept in which the arrays moves in a platform at the ceiling. And again, compared the scheme with movable decode and forward relay, which is the theoretical best full duplex, a movable decode and forward relay, half duplex relay, and we provided improvements in this case for a, again, massive MIMO scenario with hybrid beamforming. And even more recently, we did quite a lot of work on RES identification, how a user can identify the reachable risks in the environment. As you can see, we have multiple risks. The red ones are unreachable because there are some obstacles. The gray ones are out of range, and green ones are reachable ones. We developed this concept using phase shift reflection patterns similar to those base station identification in LTE networks by using some M sequences. And we developed this unique simple detection and identification scheme and showed that the probability of miss, so that the user identifies the intelligence surface as the first phase, so that it can be used, for a certain purpose. Because at the end of the day, the user needs to know which RES is available in the region. So we developed quite a lot of novel concepts and algorithms in this sense. Even more recently, we did some experimentation by dividing the intelligence surface by half, RAS1 and RAS2, and trying to identify the both parts by the user. Again, transmitting some signal. By the reflected back signal, the user tries to understand which RAS is active, first one, second one, or both, or none. So we have again derived both theoretical and experimental probability of miss and probability of false alarm for this practical scenario. So this again appeared this summer in IEEE Wireless Communication magazine. We provide a more general framework where this RAS identification might be useful, because as you can see, there are regions, if we try to embed this intelligent surface in practical systems, good signal quality regions, the different coverage zones. There are some security concerns. There are some multi-RAS zones and so on. Therefore, RAS identification might be critical. So, I mean, in the earlier studies, we used some sort of amplitude detection, but it is also possible to use some frequency detection and BS watermarking. So we developed all these three algorithms as a general framework: amplitude modulation, spectral fingerprinting, and BS site watermarking, and compared them in terms of computational complexity, robustness, and available waveforms. Amplitude modulation, as we also did in practical study, is the easiest one. What it is, computation complexity is low, but its precision is also low. It might be possible to obtain higher precision by using more advanced technologies like spectral fingerprinting, or, as you can see, BS size watermarking. And as we briefly mentioned in the beginning of the presentation, recent RAS architectures like star RAS, beyond diagonal RAS, we have been also working on that sense. And even more recently, we combined star RAS with a in an Isaac scenario in which there are users and targets at both front side and back side, in this case, and hybrid star RAS, as you can see, which can amplify signals and also pass the signals at the back side might be a solution. And this is actually how this star RAS with some sort of reflection type of amplifier might be possible in terms of circuit design. And even more recently, we have been trying to understand how we can use this intelligent surfaces in the case of some physical layer security concept, in which there is an target, it's an eavesdropper, but it also carries a malicious RAS which tries to distract the communication. And we have derived again some theoretical results and extended simulations in which we're trying to approach the scenario where there is no malicious RAS, harmful RAS in the environment. So I also remember some studies from the literature focusing on this problem, in which there are some harmful intelligent surfaces, malicious intelligent surfaces in the environment. Again, this has appeared a couple of months ago. Which site we can position the RAS? As you can see, we did quite a lot of studies in RAS, so I'm just trying to combine all of them in this quick presentation. So probably I need maybe a half day to go into details of all of these studies, but we don't have that time. So we can use BS site for simplified passive beamforming, or some RAS-aided localization and so on, or some dust zones coverage. But particularly for instance, indoor to average, indoor correction, outdoor to indoor coverage extension, or some sort of, for instance, disaster recovery, emergency coverage, and so on. In these scenarios, we need user-side intelligent surface. So our recent study provided a very comprehensive design framework in the sense how to use intelligent surfaces and so on. So I think I'm also approaching the end of my time. So we also did quite a lot of interesting studies on the integration of AI techniques with intelligent surfaces, either for some AI-aided partitioning for RAS-aided normal-C games, or, as you can see, it's an interesting study appeared last year in Systems Journal, in which we use actually spectrograms for 4G and 5G signals with RAS-aided system, and we use the spectrogram images in this famous image processing models to identify whether we have 4G or 5G signals in the environment. So with the assisting of the RAS, so it's an interesting scheme as well. Again, even more studies, recent studies, we export many other directions such as UAVs, again, disaster recovery, as I mentioned, even symbiotic radio with energy harvesting devices, and even more recently, in a Mars environment, to appear in Open Journal of Communication Society, in a Mars environment, we consider the potential of intelligent surfaces, different kinds of intelligent surfaces, fully passive, star arrays, amplifying arrays, so how we can use them in a hostile environment like Mars, how we can benefit them. So we did the simulations in wireless inside environment, this ray tracing type simulation environment and so on, to obtain this interesting results. Regarding beyond diagonal RIS, we actually relatively new in this field, but we did some initial studies to integrate beyond diagonal intelligent surface to the transmitter side. As you can see, this is the side view. We have this active antenna, and very closely positioned. We have these near field channel models here, and we have this beyond diagonal RIS with group connected elements, so that we can realize some sort of an advanced transmitter architecture, and we did comparisons with active analog beamforming and tried to approach it as close as possible. And also making comparisons with fully connected and group connected architectures. As we briefly discussed, fully connected architecture is more complex in terms of circuit topology, but group connected architecture is a compromise between complexity and performance. And we did this study. So modern base station architecture with beyond diagonal RIS, again, the same research team. So I think one of the first studies in the literature that considered the localization problem with the beyond diagonal RIS, again, as an active antenna at the base station and beyond diagonal RIS close to it. And we investigated the problem of localization so that we can minimize the position error bounds, as you can see, compared to the diagonal RIS and compared to the active antenna array. We are very close to the active antenna array, and much better compared to the classical diagonal RIS that we know. So to conclude, I think it has been almost 50 minutes. I'm not sure. So maybe 45 minutes it has been. So we covered some emerging RIS architectures like beyond diagonal arrays, amplifying arrays, star arrays, 3D arrays, and so on. So how to unlock the potential of these RIS architectures, how we can find killer applications, how we can integrate them to the network, how we can control them in real time. These network deployment challenges are still there. And complexity performance trade-offs. So certain architectures are more complex, more power hungry, more costly. So we need to clearly determine these complexity performance trade-offs. And there is this sad face here. We know that RIS will not be this integral part of initial 6G systems, but still we need to find, I think, the killer applications, the attractive RIS applications. If you ask my humble opinion, so I think I saw a couple of weeks ago some LinkedIn post from also Professor Emil, so he was also mentioning the same thing, and I fully agree. Probably millimeter wave or maybe FR3 band, mid-band frequencies, 70 to 24 gigahertz. These bands would be the critical bands in which RIS, assistance must be critical. So what will be the killer applications? As I briefly mentioned, actually I mentioned a couple of times, outdoor to indoor coverage extension, indoor localization, and communication in environments such as smart factories and so on at these high frequencies. I think this might be the critical scenarios in which RIS might be, very useful, because I think as far as we see from also our practical experiments and so on, under sub 6 gigahertz, the RIS sizes gets larger and larger, and the benefits get smaller. So probably we should target this kind of applications and operation frequencies to unlock the potential of intelligent surfaces. So this ends the presentation. This was the last slide of my presentation. So I will be happy to answer maybe a couple of questions from the floor. So thank you for your attendance.
Thank you so much, Professor. Very interesting and clear overview of activities in RIS. Any questions from the audience? Please feel free to raise your hand or type your questions in the chat. Otherwise, I will start. I was wondering if you think there are some unsolved critical problems in RIS that could prevent it to appear in future standard releases. Let's say I was thinking, for example, about the multi-operator interference problem.
It's a problem. It's a problem. Thank you, Matthew. I think you touched a very critical point. So you're exactly right. So probably operators might need their dedicated intelligent surfaces. One operator might have an intelligent surface. and it might create some interference. But yeah, if we focus on again on millimeter waves or these FR3 band, I think that interference might be manageable. But again, who will own the intelligent surface? Probably operators might have, their dedicated intelligent surfaces to be deployed. This is one problem. Network deployment issues, whether it will be transparent to the user equipment or not, this is another problem. So how to control the intelligent surface in real time, on the go, how to, identify, for instance, the intelligent surface is the problem that we focus. I think these are problems, so the problems are still on the table. So maybe this might be the reason why the operators and vendors took the conservative choice not to include, intelligent surface in the first release of 6G. But I think, for instance, we showed in certain environments, the smart factory environment, in a hostile environment like this, or maybe some post-disaster recovery, or in this kind of scenarios, I think intelligence service might have huge potential, I believe, but there are definitely problems again, how to realize them in real life. So with minimal latency, with minimal interference to the other users and so on. So maybe we need to solve these kind of interesting problems.
Yeah, thank you so much.
Thank you.
Okay, any other questions? Okay, if not, let us thank again the speaker, Ertugrul. Thank you so much.
Thank you. Thank you, Matthew.
And the recording will be probably available on YouTube, and I'll see you if you want. Next week we will have the 5th talk of the webinar series of BD-RIS. Thank you so much, Professor.
Thank you.
Bye-bye.
Thank you, Matthew. Have a nice day. Bye-bye.